All right, so the first question that we asked in the last video was that if f of xy is the density of the rectangular region R at the point xy, then what is the mass of R? Now, if f of xy is a constant function, then we know that we can just multiply the constant density with the area of R to get the mass of R. However, density is varying maybe, so how do we go about approximating the mass of R? Well, even though the density is varying, one idea I'm pretty sure that you have indulged in your mind when you were thinking about that question is that break up the region into tiny pieces. And the reason that's a good idea is that if I break the rectangle into tiny pieces, then the density over a tiny piece, even though varying, but can be assumed to be almost a constant. So if I have so the density over a tiny piece would be approximately constant. So think about breaking R into thousands and millions of pieces. So then the density over a tiny piece is approximately constant. So that's the main idea that I want to use here. So let's say, so here is our rectangular region R. So it is given by the interval from A to B along the x-axis, in interval from C to D along the y-axis. So here's how we're going to break up this rectangle into tiny pieces. So I am going to, first of all, divide this rectangle into vertical strips. So let's say we're going to divide this into m vertical strips. So these are the vertical strips. So that is, notice that I'm breaking up this rectangle along a x1, x2, x3, xi minus 1, xi, xn, which is b. So if we draw these vertical lines at x1, x2, and so on, that's going to break up the region R into vertical strips like this. So let's say we have m vertical strips here. Similarly, now we are going to break up the rectangle into horizontal strips. So we are dividing it at y0 is equal to c, and then we are drawing a horizontal line at y1, horizontal line at y2, horizontal line at yj minus 1, yj, the horizontal line at yn, which is d. So after we draw these horizontal lines, they will divide the region R into n horizontal pieces. So we have n horizontal pieces here and m vertical pieces here. So together they divide the rectangle R into m times n subrectangles. Okay, so those are our tiny pieces. So these subrectangles are our tiny pieces. So if I pick the ith vertical strip here and the jth horizontal strip here, then the subrectangle that we get here, I'm going to label that Rij. So this is my ijth subrectangle, where I is between 0 and I is between 1 and n, and j is between this should be an m here. So I is between, so we're looking at the subrectangle Rij, where I is between 1 and m, j is between 1 and n. And okay, so this subrectangle Rij is so tiny that the density over this subrectangle is approximately constant. So I can approximate, so I can pretty much say that, okay, if I pick a point in this subrectangle, which I'm labeling as xij star, comma yij star, so this is a point in the ijth subrectangle here, then I can say, well, that f of xij star yij star is the density of this is the density of Rij at any point approximately. So if I multiply that by the area of Rij, then this product is going to give me, so this is density multiplied by the area, so this is going to give me the mass of Rij. So this is notice that that's the same as f of xij star yij star, and area of Rij I'm going to just call the delta Aij, and this is approximately the mass of Rij. So again, the idea is that, so we divided the rectangle into m vertical strips and n horizontal strips, and then I'm focusing on the subrectangle that is given by the ith vertical strip and the jth horizontal strip here, and I'm calling that Rij, and I'm taking a point here which I'm labeling as xij star yij star, and assuming that this is very tiny, we can assume that the density over this subrectangle is constant. So then if I multiply the density at this test point here with the area of this subrectangle, then that should be a approximate value of the mass of this subrectangle. So we can do this for every single subrectangle, and then we can add them up to come up with an approximate value of the mass of the entire rectangle. So the Riemann sum, so this the way that we partitioned the rectangle R, the way we divided the rectangle R into subrectangles, that's called a partition of the rectangle, and I'm denoting that by P. The Riemann sum of f on the rectangle R with respect to the partition P is basically this sum where notice that this if f is the density, then this is the mass of the ijth subrectangle here. So by doing this sum, we are basically summing over all the subrectangles. So recall that I is going from 1 to m and j is going from 1 to n. So j is going from 1 to n and I is going from 1 to m. So basically what it means, remember, I means here, the range for I, basically I goes over the number of vertical strips, and j is going over the number of horizontal strips. And so this sum here is an approximate value of the mass of the entire rectangle R. Now notice that the area of the ijth piece, so area of this piece right here, well, that's a delta x, which is the the width of this vertical strip and multiplied by the width of this horizontal strip right here, and so that's delta y. So if I multiply delta x delta y, that's going to give me the area of this piece. Okay, so notice that obviously, so this sum is an approximate value of the mass of the entire rectangle R. Notice that our approximation is going to get better and better if these pieces are tinier and tinier, right? So the tinier the pieces are, the better our approximation of the density is. So then it makes sense that we define the actual density of R to be the limit as mn goes to infinity of this Riemann sum. And this limit is the definition of double integral of the function f over the rectangle R. Okay, so then we have answered our first question in the previous video, which is how do we calculate the mass of the rectangle R if f of xy is the density function. And the answer is that the mass is given by this limit of this Riemann sum, and then we are defining this limit to be the double integral of f over R. Now let me ask a question before I stop the video, which is what happens when the density function is just 1? Well, if the density function is just 1, then what can I say about this Riemann sum right here? Well, notice that if f is a constant function 1, then this quantity here would be 1. So then we are summing the areas of the subrectangles, right? So then the Riemann sum is based when f is just 1, then the Riemann sum is basically summing the areas of these subrectangles. Well, if I am summing the areas of these subrectangles, then I should be getting the area of the entire rectangle. So notice that if the function f is 1, then the Riemann sum here is just simply going to give me the area of the rectangle R. And so you can see once again is that in this picture that so if f of xy is 1, then the Riemann sum is going to be, so if f of xy is 1 for all xy, then the Riemann sum that we had would be 1 times the area of the ijth subrectangle. And so this is I going from 1 up to m, j going from 1 up to n, and this is going to be equal to the area of the entire rectangle. Okay, so we have answered our first question, and I really encourage you to think about why it is reasonable to define the density by using this sum. And our approximation method is a good one because obviously we can make our approximation better and better simply by dividing the rectangle into tinier and tinier pieces. Okay, so let me stop the video here, and we will be tackling the the second question in the next video.